we've got multivariate calculus now. We want to extend the concepts that we had in Calculus 1. Here's a major one, right? The area under a curve. If we have y equals f of x, a function of one variable, all right, we can estimate the area under the curve. If f of x is non-negative, we'll say the area under the curve. By breaking up the interval from x0 equals a to xn equals b into n subintervals, from x0 to x1, x1 to x2, and so on. And we'll do that by calling this width delta x1, this delta x2 up to delta xn. And we'll take the height at some intermediate point, x1 star in the first interval. And so the area of the rectangle is delta x1 times f of x1 star, right? And the area of the second one is delta x2 times the height f of x2 star, and so on. And you add all those together, and we said the sum, we call this a Riemann sum after the famous mathematician Riemann, one of the students of the great Gauss actually. Died young of tuberculosis, unfortunately. He might have been as great, I don't know. Sum k equals 1 to n of n rectangles. This is the area of the kth rectangle, right? Here's its height, f of x k star. Here's its base, delta x k. So height times base of the kth rectangle, sum k equals 1 to n rectangles. That's what we did in Calculus 1. And we said that's only an estimate. What good is that? Well, if you make a lot of little rectangles, you can get a pretty good estimate, right? And in fact, in the limit, as the number of rectangles goes to infinity, here it is, the same formula, but take limit as n goes to infinity, where we let the width of the widest interval go to 0. We define this, actually, to be the definite integral from a to b of f of x dx, and say that for f non-negative on the interval, this is actually the area under the curve. Why? Because it turns out that you can show at the limit of the sum, whether you take a little inscribed rectangle, taking the lowest endpoint in each interval, maybe rectangles like this, and you add all those up, and the circumscribed rectangles, where you take the highest point in each interval, a rectangle like that, a rectangle like that, a rectangle like this. If you add up that limit, you get the same number in the limit as n goes to infinity. The overestimating areas limit and the underestimating areas limit add up to the same number, as does anything in between, like we drew here. Here maybe we took the midpoint of each interval, and we add all these up. All those limits, for a continuous function at least, come out to have the same value, and so we'll just define this to be the definite integral. We'll say for a continuous function f of x, the definite integral has this definition, and if f is non-negative on the interval, then this will also be called the area under f of x from x equals a to x equals b. So that's a good reminder, I hope. I know you've seen that all before, but it's very important to understand that concept, because now we want to do the same thing for a function of two variables. Here's my MATLAB generated surface here. And suppose I want to find the area under the surface over a rectangle. X goes from a to b, and y goes from c to d. So there's a rectangle, a to b and c to d in the xy plane. What's the area beneath this surface z equals f of xy that sits over that rectangle? Suppose z is non-negative. Well, we can do the same kind of thing. We just got to break it up into little rectangular boxes this way. We know what their volume is, right? And we'll find the volume under the surface. The base is delta xj times delta yk if we take the jth increment in the x direction and the kth increment in the y direction. And so delta xj times delta yk times f at some intermediate point in the base here, f of xj star yk star, you can kind of see the little faint line going up the middle, will be the height. So length times width times height gives you the volume of the little box, and you add up using m increments in the x direction and n increments in the y direction. Little n equals m times n subrectangles, right? And it's an m by n grid. And so we can take the sum, k going from 1 to n, the number of y increments, j going from 1 to m, the x increments, sum over all these little rectangles of base area, delta xj, delta yk. Sometimes I'll just write this delta a, jk like this. F of x j star, y k star. And so this is the volume of the jk box. And then this is the height of the jk box times the base. Now when you add all those up, you get an estimated volume under the surface. What happens in the limit is the number of little rectangles in the bottom goes to infinity. If you have a continuous surface and you let the width of the smallest interval in both directions go to 0, then it turns out that this limit of the sum of these parallel pipets, we call them, rectangular parallel pipets, or rectangular boxes. The sum of the rectangular boxes in the limit goes to the same number whether you overestimate or underestimate over each region. It doesn't matter, you get the same limit. So we'll define this to be the definite integral of a function of two variables, and we'll say because of that nice theorem, and the limit is the number of subregions goes to increments in both directions goes to infinity, with the widest in both different directions going to 0. Sorry, we get the same number. So this makes sense to define it this way. All right. So there is the definition of the double integral over a rectangle R. We write it this way: double integral over R f of xy dA means this. Just like in calculus 1, when you wrote this was notation that meant limit as n goes to infinity, sum k equals 1 to n f of x k star delta x k. That's what it meant. It's this limit that is the area under the curve for f non-negative and continuous. Just so, so there's some calculus 1. This notation will mean this limit. All right. So that's, so you understand what the thing is meaning. Sometimes if you don't understand what it means, you just, you never know when you can use it. I had that terrible trouble in physics. I would not understand when I could use the formulas until I went and took my math class. Then I would understand when it worked and when it didn't. So that's maybe true for you too. Here's the nice theorem, which we already sort of stated. If f of x, y, a function of two variables, is continuous on a rectangle R, then it's integrable over R. What does integral mean? It means that this limit of the sum exists and gives you a fixed number. Exists means that regardless of how you break up the partition and whether you use and what points you use in the intermediate parts, you get the same number. The limit exists and you get the same number. All right, so this function is integrable when it's continuous over the rectangle. Now, furthermore, there's nice formulas, and just like in calculus 1, you didn't use that klutzy formula definition to evaluate your integrals. You then wrote down theorems that could be proved with that definition and used those, like the integral of the sum is the sum of the integrals for continuous functions. You can pull a constant out of the integral. All of those kind of nice things. Integral of x to the n is x to the n plus 1 over n plus 1, and then you can plug in the endpoints and take the difference according to the fundamental theorem of calculus to evaluate the. So you had the value of integral x squared from a to b. Similarly here, we'll do the same thing. One of the theorems is that the sum and difference of double integrals of integrable functions is again integrable, so it includes continuous functions. And a constant can be pulled out of a double integral, just like in calculus 1. And furthermore, here's a wonderful theorem, because how did we evaluate integrals in calculus 1? We used the fundamental theorem of calculus that you could take an antiderivative, right? This integral of x from a to b, you took x squared over 2, plugged in b and plugged in a and took the difference, right? So that was the way we could evaluate those without having to go back to that horrible definition that's hard to evaluate anything. How can we make an easy way to evaluate double integrals now? It works like this. Fubini has a theorem that says if f is continuous over a rectangle, this notation means that this is the integral x going from a to b, the integral y going from c to d. This is the Cartesian product, so it means the set of all ordered pairs where x comes from this interval and y comes from this interval. So this is the rectangle, right? So it's fancy notation for the rectangle, x going from A to B and y going from C to D. If f is continuous over the rectangle, then its double integral exists and is equal to the iterated integration in either order, actually, in which the inside integral is a partial integral, treating the outside variable as a constant. Of this form, you can integrate with respect to x on the inside, plug in a and b and take the difference, using, since it's a single integral, you can use the fundamental theorem of calculus like you did. You just treat y as though it was c. You integrate this with a constant c here, and then you put back in y afterwards. That's the partial integral. Just like partial derivatives amounted to treating y as a c, taking the derivative and then putting y back for c. Similarly, the integral, you can put in c for y, integrate with respect to x, and then put back y. All right, so that's what the partial integral means, and then you integrate with respect to y on the outside. Because you've evaluated x at the endpoints, this is just a function of y, so the outside integral is an ordinary calculus 1 integral. So you do a partial integral on the inside, treating y as a constant, and then an ordinary integral on the outside, and evaluate the double integral without having to go back to that terrible limit of the sum. You just need to understand what it's computing so you know when you can use it. But this is how we evaluate it, just like in calculus 1, you use the fundamental theorem of calculus. Now we'll use for double integrals Fubini's theorem, if the region is a rectangle, and do this with the inside integral, partial integral, and the way we evaluate these is again with the fundamental theorem of calculus twice. Now the theorem also says you can do it in the other order. You can integrate y going from c to d. This is one integral, and then there's an integral of an integral. So you integrate y from c to d, treating x as a constant, just doing ordinary integration, and then you do an ordinary integral. This becomes just a function of x, and you do calculus 1 integral of that. All right, so there's how you deal with rectangles. Now, here's an example. Suppose maybe I wanted to find the volume below the surface, z equals 2x plus y, that sits over the rectangle in the xy plane, x going from 0 to 1, y going from 1 to 3. You can imagine what this looks like pretty easily. Just to draw a picture on the board just quickly. Here's the region. X going from 0 to 1, y going from 1 to 3 is this region here. And actually, let's just leave it like that and say, now over that region, here's x, y, and z. And the xy plane, y goes from 1 to 3. X goes from 0 to 1. And so you've got this little rectangle here in the xy plane, and you want the volume below the surface, z equals 2x plus y. Well, it's, if you think about it, z equals 2x plus y is a plane, right? Ax plus by plus cz equals d is always a plane, and that's what z equals 2x plus y is. And moreover, it goes through the origin, and so this is the volume below a plane that sits over this region. Something like this. So it's a volume of some kind of solid like this that has a plane on the top, a crooked plane, and then it's rectangular base and sides that are trapezoids like that. So what's the volume under there? We can estimate it just using the Riemann sum we mentioned above without taking the limit. So we could say, compute the Riemann sum for this. Well, it's the sum. If I use this grid where I break x into 1 increment, y into 2 increments, then it's just the sum over two rectangles, right? J goes from 1 to 1. I just do 1 increment in the x direction, and then k goes from 1 to 2. I do 2 increments in the y direction, two rectangles, or two intervals, and I sum the height times the width times the length, right? And so here's when k equals 1 and j equals 1. Here's when k equals 2 and j equals 1. You just have to add those two together. This segment notation means this. And now I made decimate each interval with 1, so I replace delta x1, delta y1 with 1 each, and add those up, and then the height, let's just take the midpoint of each, that's what those dots are for. So I'll take f at x equals 0.5, y equals 1.5 for the height of a rectangular parallel pipet over this region, and f at 0.5, 2.5 this point for the height over the second rectangular region. And so we can add up two boxes, one over this region, so we take a rectangular box and another rectangular box, add those up and say those are approximately, the sum of those two things are approximately the volume below the plane. And this is 2.5 plus 3.5, we wind up with 6 for our estimated volume. Well, what we just saw is actually there's a formula for doing this. Let's see. For doing this exactly, provided we can do the integrals. Suppose I want to find, let's say this time, the exact volume. I can find the exact volume with a double integral. I simply write double integral of the function that I want the volume below, dA, and this is the notation that we use if we want the volume below z equals e to the x cosine y, we just put double integral e to the x cosine y, dA. And suppose we want it over this rectangle, x going from 0 to 1, y going from minus pi over 2 to pi over 2. Well, Fubini's theorem says that we can integrate between the x endpoints on the outside with respect to x on the outside, and between the y endpoints on the inside with respect to y on the inside, where we make the inside integral a partial integral. So if this is a partial integral, then x is treated as a constant, e to the x is a constant. We can pull a constant out of this integral. So I'll pull the e to the x out because it's treated as a constant. I'll pull it in here, and then what's left in here, once you pull the e to the x out, is the integral cosine y dy evaluated at 2 endpoints. Right, this without the e to the x in there is just a constant. When you plug in the endpoints, take the difference, it's a number, and the e to the x is out. So you pull the e to the x out, and you integrate a constant. Well, you can pull the constant out of the integral. So you can pull the y integral over here, and just integrate the product of these two integrals. Integral of e to the x dx times the integral cosine y dy by pulling e to the x through here into here because it's treated as a constant in the partial integration. And then because the integral from minus pi over 2 to pi over 2 of cosine y dy is just a number, you can then pull it out of the x integral. And there you go, the product of these two integrals. And lo and behold, calculus 1, right? This is integral with respect to x, this is integral with respect to y. We evaluate them using the fundamental term of calculus. The antiderivative of e to the x is e to the x, it's its own integral, right? Integral of cosine y is sine y. We plug in the endpoints. Oh, there's a typo. This should have said 0 to pi over 2, I guess. Oh, no, I'm sorry. Let's see. I'm sorry, I did one more thing. Thought I had a mistake. Instead of going from minus pi over 2 to pi over 2 cosine y, cosine is an even function, right? The integral from minus anything to plus the same thing is twice the integral from 0 to the top. So this is twice the integral from 0 to pi over 2, so I'll put a 2 out here and integrate from 0 to 2 instead. That's a symmetry thing that's really useful, just like it was in calculus 1. And now I take sine, evaluate at these endpoints, take the difference, e to the x at these endpoints, take the difference, multiply the whole thing by 2, because that's what I just did. And I get 2e minus 2 is the exact volume below this messier surface, actually, over this rectangle. How about that? So we're getting to do some very interesting problems, right? We can calculate areas in calculus 1. Now we can calculate volumes, right? Really useful thing. In fact, this calculation can allow you to get all sorts of neat volume formulas that you see for volume of a sphere, volume of a cone, all these kind of things. Surface areas, too, are coming up. Neat results you get out of this, but we need a little bit more. We want to do non-rectangular regions, for instance. Here's non-rectangular regions. If we have a closed bounded region, closed means it includes its boundary. Bounded means it doesn't go off to infinity. There's some circle, no matter how big it has to be, that encloses the whole thing. It doesn't go out to infinity, then it's bounded. So if you have a plane region R that's not a rectangle, product, little n equals m times n, of the same thing. K goes from 1 to n, j goes from 1 to m. F of xj star, yk star, delta xj, yk, delta yk. What's changed? It doesn't look much different. Here's what's changed, this little hat here. F hat is equal to f of xy if you're over an enclosing, if you're over the region R that's not a rectangle anymore, then you take the height of the function, and if you're not over the region R which the function is defined, you take height 0. So it's like this, and then what this means is you actually enclose the closed bounded region with a big rectangle. So here's your region of definition for the surface, this little oval in the xy plane. There's a surface over the top. You say, I wonder what the volume is below this surface and over the oval in the plane. What you do is you enclose it in a big rectangle. You do the sum over the rectangle of the heights of the little rectangular parallelepipeds, or the volumes of the little rectangular parallelepipeds. And the only thing is, if you're at a point, if in a rectangle you choose a point in here that's not in the oval, then you take height 0 and you just get no volume. Same thing here. But if you pick a point here that's in the oval where the surface is defined, then you take the height of the surface. And as the number of regions goes to infinity, it turns out this gets the same number regardless of how you do it for a continuous function of two variables. And so this is the way you want to define the volume below the surface and over this non-rectangular region is enclose it in a rectangle, and do this. Take 0 height when you're outside the domain of the surface and take the height of the surface when you're inside. And now we can calculate volumes below surface if we just evaluate this limit. Well, wait a minute, Fubini's theorem doesn't work anymore. It was only for rectangles. What do? Well, suppose you have a type 1 region, sometimes called a vertically simple region because you got vertical sides here, or a type 2 region. Suppose you have horizontal sides, sometimes called a horizontally simple region. Then you can say that this double integral of a continuous function exists for this non-rectangular region. And what's more, it's equal to an iterated integral like we did last time. It's just that the endpoints on the inside integral are not constants anymore. They go, for a type 1 region, if you go from y equals g1 of x to y equals g2 of x, bottom curve to top curve, then you integrate from g1 of x to g2 of x. Variable endpoints, right? If you're in a type 2 region, a horizontally simple region, then you integrate from the left curve, x equals g1 of y, to the right curve, x equals g2 of y. And then the outside between y equals c and d, the constant endpoints, just like before. All right, so now, because of this theorem, we can evaluate double integrals and hence volumes over, and other things, over non-rectangular plane regions. Suppose I want the volume, for instance, below the plane z equals x plus y that sits over this triangle in the xy plane. And so if you draw the picture, you put this triangle down the xy plane and you want the volume below the plane that's over this. How can I evaluate that? Because now the base is no longer a rectangle. Well, we say it's the double integral over r, x plus y dA, that's the height of the surface dA. And on the outsides, if I treat this as a vertically simple region, right? That means you have a function on the bottom, y equals 0, a function on the top, y equals, if you figure this out, suppose it goes from 0, 1 to 2, 0, then this is a straight line, because right, it's the edge of a triangle, and it's got slope minus a half because you go down 1 and over 2, and it goes through 0, 1, so you use the slope-intercept formula, right? Y equals mx plus b, where b is the y-intercept 1, and slope m is minus a half, so g of x, g2 of x equals minus a half x plus 1 is the equation of the top curve. Y equals 0 is obviously the equation for the bottom, so on the inside integral I go from the bottom surface, bottom line, y equals 0 to the top line, y equals minus a half x plus 1, or I'll write it as 1 minus a half x. That's all I have to do instead of going between two pairs of fixed points. Only the outside endpoints are constants, and the insides are the equation for the bottom curve and the top curve. Or if you do this type of region, then you integrate in the other order. Y on the outside, x on the inside, go from left curve to right curve on the inside. All right, so there it is, and I just have to integrate this. How did I do it? Well, the inside integral is a partial integral treating, since I'm integrating with respect to y, x is a constant, so I integrate x with respect to y, and I get xy, right, because it's constant. It's partial integral of a constant. C is c times y, so a partial integral of x is x times y, treating x as a constant. However, integral of y is 1/2 y squared, because y is not constant, right? All right, so that's a partial integral, just undoing partial derivatives. Take the partial derivative, you get x plus y back. And I have to evaluate that at 0 and 1 minus 1/2 x, and I get this. And now what I have is an integral with respect to x of this mess, but it's just a calculus 1 basic integral of a second degree polynomial. 1/2 plus 1/2 x minus 3 is x squared. You integrate that and come out with, oh, this has unit volume actually. How about that for a curve problem? So the area of this solid, the volume of this solid is 1. Let's see, that's the wrong one. That's all I want to cover for today, I think. Give the homework problems a try, and let me know if you have questions.